exciting work. Okay. Let me just click on. Yeah, so today I'll talk about towards preparation of scattering wave packets of hadrons on a quantum computer. This is a NISQ algorithm for lattice gauge theories, which came out very recently. This is a work done with my former advisor, Professor Zoe Dawudi at the University of Maryland, and her current grad student and my collaborator, Changchun Xie. So I tried to cut down a lot of basic stuff from this slides because the audience is very much familiar with it, especially this audience. But if you find some things which are pretty basic, bear with me just because I made the slides. All right, so what should we care about gauge theories? So first of all, of course, standard model is made up of gauge theories. It's made up of SU3 cross SU2 cross U1, and forces in the standard model are described by gauge theories. Especially the weak and the strong force that are described by non-abelian gauge theories, and particularly the strong force which is given by quantum chromodynamics, theory which describes nuclear forces while interacting quarks mediated by gluons, is a SU3 color non-abelian gauge theory, and it becomes strongly interacting at low energies. And it exhibits a phenomena called confinement, where the degrees of freedom of the low energy theory are different than the fields which are describing it. And it requires non-perturbative methods for calculating observables at such low energy. So the current best method that we have is a numerical method of solving QCD non-perturbatively, which is known as lattice QCD, where you start with the path integral formalism with a weak rotation in Euclidean time, and you discretize it. And this path integral then acquires a interpretation of a probability distribution over the gauge fields, and you generate these gauge configurations, create the probability distribution, and measure the observable that you're interested in. And so far, this method has shown tremendous success. It has calculated hadron spectrum and predicted some exotic states. It has calculated hadron form factors, values of quark masses, and the strong coupling constant. And also, these are all kind of static quantities, and some. It has also there's also ways to obtain dynamical quantities like scattering phase shifts and decay rates with a formalism called Lucius formalism. However, it has certain shortcomings, and the very famous one, the notorious one, is the sign problem, where if you try to calculate the QCD phase diagram, this probability distribution function interpretation of the measure goes away, and then you have some oscillating behavior here, which you cannot capture in a reasonable time. The formalism is in Euclidean time, so anything related to the real-time evolution and the real-time dynamics becomes extremely difficult to extract. Even though I told you that it's possible, it gets tedious as you go high in more and more particle processes involving more and more particles. That's why many-body processes are also harder to obtain. Is there an alternative? Yes. It's called the Hamiltonian formulation, where you start, where you calculate observables by just calculating their expectation value. Start with the state, evolve it with the Hamiltonian in time, measure the observable you want to measure, evolve it back, and take the projection. Manifestly, since it doesn't have any probability distribution interpretation, it has no sign problem. The time is real, so real-time processes become easy to obtain. And there are also ways to obtain imaginary time evolution, but I'll not go into that. And since the entire Hilbert space is available because of its construction, many body processes and scattering are inbuilt in its construction. You don't have to do anything different. But there's a downside, and the downside is that the Hilbert space scales exponentially with the system size. Is there a way to deal with this number 4? There are some, and today I'll be talking about this particular one, which is called quantum simulation. So what saves in a quantum simulation, particularly this is variation which we call digital quantum simulation, is the fundamental ingredient of your simulation is a qubit, which is a superposition of an up and down state, or 0 and 1. And if you stitch together n such qubits, then you get a superposition of 2 to the power n states, and this is where the exponential scaling helps you. And I will particularly talking about the problem of scattering on a quantum computer. And this is a schematic protocol of scattering, where the first step is you encode the degrees of freedom of the theory that you're interested in on these qubits, and you start with a known state. Then you prepare a scattering state by some state preparation algorithm. Then you perform the unitary time evolution, which is the e to the power IST, and that takes qubits to a particular configuration. You measure it, they collapse into zeros and one, and these are the classical resistors where you show them, where you store them. And this entire process done once is called a shot, and this is an example of two shots where you get two different outcomes. You can get many different outcomes, and you collect them all, and that's how you get the probability distribution of each state into this 2 to the power n number of states available. Okay, and today I'll be talking about the this part, which is the state preparation and how to prepare a scattering state on a quantum computer for a scattering problem. So in this pioneer work by Jordan Lee and Preskill, they gave one method where you start with an interacting ground state, shown here by omega 0. And since it's a since we start with a non-interacting theory, the form of raising operators or AK daggers, which create a one particle state, is known. And because of these known operators, one can construct whatever wave function that you want to create and create a wave packet out of it by just acting it on the non-interacting ground state. The next step is to perform an adiabatic evolution by slowly cranking up the interaction and then slowly taking this non-interacting wave packet and deform it to an interacting wave packet. There are some shortcomings to this. First is the resource cost. It's extremely expensive, especially for the NISC-era devices, to perform all these processes just to come at the starting point. Second, if there are phase transitions in this evolution, then you get long-range mode and your adiabatic slow evolution fails. And particularly for the problems like confinement, where the degrees of freedom are different than the free degrees of freedom, it becomes harder to map what is the starting wave function in terms of this non-interacting theory and what is the final wave function that you want to obtain in terms of this confined degrees of freedom. Here are some other a quick snapshot of the literature survey. This is a hot topic, and there are different methods of preparing states. Some are adiabatic, some are non-adiabatic, some are digital, some are analog. It's not an exhaustive list, just a sample that the people are actively thinking about this problem in various contexts. Our approach is to create the single particle creation operators directly into non-interacting theory based on an ansatz. So I'll denote this ansatz by BK dagger. We'll start with the interacting ground state, just like the non-interacting, just like this parallel picture here. Use an ansatz to build the interacting creation operators, act it on the interacting ground state to create this interacting wave packet. This approach is motivated by this paper by Rigobolo, Notar, Nicola, Magnifico, and Montangelo. I probably butchered everything. Sorry about that. But in this work, they use this approach for tensor network methods. And we use that as a starting point and modify it a little bit to match it with what we are trying to do with the on a quantum simulator. All right. So this is the outline of my talk. I'll first go over what model I'll be dealing with, which is the Z2 lattice gauge theory in 1+1 dimension with dynamical matter. I'll talk about the methods, how to construct this creation operator, the mapping, how to design the quantum algorithm and the circuit, the measurements, results from the continuums H11 system, and moreover, which is what I'm thinking about doing. Any questions so far? Excellent. All right, so model. So this is Z2 lattice gauge theory in 1+1D with dynamical matter. And why we're starting with this theory, first of all, it's confined. So that kind of mimics to what the ultimate goal is, that is simulating CCD. And also the other nice feature is that the Zn theories, when taken to infinity, approach to the U1 abelian lattice gauge theory, which is the Schwinger model, which also exhibits confinement and historically was one of the first models to study confinement in detail. The starting point would be, the time would be continuous and the space would be discretized into lattice points. However, since there are fermionic degrees of freedom and there are issues with having the correct mapping of fermions on the lattice to take the correct dispersion relation in the continuum limit, we use the staggered formalism where each physical site is split into two staggered sites. And the fermionic degrees of freedom are split according to the matter and the antimatter part. The matter part lives on the even side, and the antimatter part lives on the odd side. And it has a Dirac-C interpretation to the Hilbert space, meaning the matter side, when empty, has no particle, and when filled has a particle. But for the antimatter side, it's opposite. When it's empty, that means there is an antiparticle excitation, and when it's filled, there's no antiparticle. And from staggering, you acquire this mass term for the Hamiltonian, where you have the oscillating sign coming from this matter and antimatter splitting. The next, bosonic degrees of freedom, which live on the link connecting two staggered sites. Since it is Z2, it is like a qubit. It has two states, up and down. And one would be the excited state. One would increase the energy compared to this electric field Hamiltonian energy, and the other would be lowering it. Combine the fermionic and the bosonic degrees of freedom interact via this interacting term, where every time a fermion is hopped between two staggered sites, the gauge link in between is split. So this is the complete Hamiltonian with three terms. And naturally, one would ask, okay, so these are the degrees of freedom. Are all 2 to the power 2n states physical states? The answer is no, because in order to obey the gauge invariance, which is the feature of the lattice gauge theories, one needs to implement constraints on the Hilbert space known as the Gauss's law. And in this case, the Gauss's law is given by this condition where the operator acted on a physical state. If it is identity, then that state is a physical state. And this operator is given by this form, which physically has this interpretation where every time there is a particle or an antiparticle excitation, it will flip the gauge field. So this is the pictorial representation. We work with periodic boundary condition and with charge zero sector. That means total number of particles and total number of antiparticles are taken equal, because we're interested in ultimately in the U1 theory, and this is the sector which matches taken to the n to the infinity limit to the U1 sector, the U1 periodic boundary condition sector. And because of this, what happens is that the number of physical states are significantly lower than the overall possible state, as shown here for the 4th site and the 6th site theory, where the possible states are large, but the physical states are extremely a tiny fraction of the overall Hilbert space. And for this work, we would be dealing with 6 staggered site theory. So I would like you to remember this number 40, which will appear later in the results. And gauge invariance also demands, or the satisfaction of the Gauss law condition also demands, that all types of excitation, starting from this something called a strong coupling vacuum, where there are no excitation, no fermionic excitations, and low energy boson configuration. The only excitations possible are something we are referring to as a mesonic excitation, where that means you need to flip. If you hop a fermion between staggered sites, then you need to flip the corresponding gauge links everywhere else, and this will make sure that the states remain in the physical Hilbert space. This is an example of a length 3 meson, where the starting is a particle side and the ends and an antiparticle side, and the gauge links in between are excited. So, any questions? All right. So, method. Yeah.
Just a quick question. So, your physics containing the non-zero charge?
So the Hamiltonian respects the symmetry, so it stays within that sector because it's just fermion hopping. I don't know what you mean by non-trivial, but it is certainly not the sector which gets mapped to the U1 sector, because U1 sector, if you impose, for the U1 theory, if you impose periodic boundary condition, it necessarily means charge zero sector. So if you want to take this limit, then there might be other things happening in the non-zero charge sector, but the periodic boundary condition limit of the U1 is the zero sector, so that's why we are restricting.
So in the U1 case, there is no overall charge going around, like a current.
If it is a periodic boundary condition, then you have to end at the same gauge link where you started with, and every particle or an antiparticle will raise the electric field. And since it's unbounded and it can go to infinity, you have to come back to the same point that you started with. That means the number of particle excitations and the number of antiparticle excitations in the lattice has to be equal.
Yes.
Yeah. Right. So that's why there is no net charge in that sense. for the lattice with the
Okay.
periodic boundary condition.
I see.
Yeah.
That's what you mean.
Yeah.
But there could be a global flux.
You mean the windings of the there can be windings, but I mean charge sourced or synced by the particles. Yeah.
Question.
Yeah.
So for U1, you can have a theta term. For 2 pi half, you actually decompile.
Yeah.
How do you get a theta term in the infinity?
How do I get the theta term in the n to infinity limit?
Yes.
I don't know. I have never thought about it. So the theta term is some kind of a topological term, right? It has a topological origin.
U1 is just a constant electric.
So I haven't thought about it, the theta term in terms of Zn, but maybe something I'll talk about later. Yeah. All right. So let's talk about the ansatz in detail. As I mentioned earlier, the starting point is this an ansatz for the BK dagger, which will excite one single particle state from the interacting ground state. And it has this algebraic form, and we will look at each and every component. So this B part has a decomposition in terms of, so first of all, a BK dagger is a sum over these momenta P and Q, which are the lattice, the physical momentum, the physical Brillouin zone momenta. And the B has decomposition in terms of these string-like objects. When put together, will give the mesonic terms. What do I mean by that? So it has these factors which are coming from taking the free fermionic fields, and these are the kinematic factors from exactly solving the free fermionic theory. And what is different in the gauge theory is just this string of gauge field flips, which will make sure that this object has a gauge field excitations coming to the right. Similarly, for the antiparticle side, gauge field excitations to the right, and when put together, it will have it will create the mesonic excitations with the kinematic factor combined from these two different components, such that the B operator makes sure that it stays within the physical Hilbert space because it only creates the mesonic excitations. The projection operators make sure that it has the P and the Q momentum for the individual component, and the next part, which is this delta function, shows that the sum of this independent components is the momentum that you're interested in creating. Finally, there is this ansatz which borrowed from this paper, is a Gaussian ansatz in terms of P and Q, which are the independent momenta of the particle and antiparticle. And this has a phase which kind of ensures where is it centered at. And the second part is this Gaussian profile between P's and Q's. That means when we're adding the two momenta to get the momentum K, if they are further apart from each other, they are suppressed in their contribution. Closer they are to the addition, higher is the contribution. And here's an example for K equal to 0. So this is the ansatz. And these are the two parameters which we are taking as something to be optimized to make sure that the ansatz has the maximum overlap with the single particle momentum state. So we're going to optimize the mu k and the sigma k by creating a k momentum state using this BK dagger and minimizing its energy. Since the form of this BK dagger is designed in a way that it remains in a particular momentum sector, we know that this EK for non-zero momenta it always stays, always is the lowest energy state possible that you can have. For K equal to 0, we try to optimize it with VKE such that it has 0 projection on the interacting ground state. But in many cases, we realize that it's not needed because just by the nature of this BK dagger, since it's exciting something on the interacting ground state, which each component has higher energy, you will always get something which is orthogonal to the interacting ground state. So just by optimizing this, we can obtain all the first excited states in the respective momentum sector. We did this classically, but we checked with the VQE method and by designing a circuit for it, and it works. We also did it for the U1 lattice gauge theory in 1+1 dimension, but we didn't put it on hardware because we were limited by the resources we had available at the time.
Number of shots or number of qubits?
Everything, number of qubits, number of shots, the amount of CNOS that we need to put in order to create anything. And by that time, the device becomes too noisy and all that.
What's the phase factor in the eta too? The e to the I, p minus q, mu, a.
So it's kind of a centering in the K space. I don't have a really good answer about how do I see it. How do I exactly see it? What we have observed most of the time is very close to zero. So yeah, this is something which is borrowed directly from them, and it has worked for the, so we don't know if for maybe very large, so in this work, they didn't optimize a parameter. They just took it as an ansatz and used these two as input parameters and showed that it still forms a state which is, which doesn't disperse away if you evolve it in time. So we don't know if we try to do it for the large lattices, maybe the centering will matter. But it's so far observed that it always gets close to zero.
So if mu is 0, you're building a real wave function.
Sorry, so this is not to the wave function part. This is just the.
But if you add BK dagger on the strong coupling vacuum
and try to optimize it.
and you get mu is 0, are you going to have a real wave function for your wave packet?
For the wave packet, we can also have a different phase which will make sure. So there is an overlap. So these are the K momentum state, but there is also a dressing function which is also taken Gaussian. So this can introduce phases in the momentum space that we want. So this wave packet is created by stitching this wave function to each K state. And even if mu is 0 here, between each K state, I can introduce this phase by hand, which is this outer dressing in the momentum space. Okay. And these are inputs. So this is again taken a Gaussian with some phase. So this will make sure where is it centered in the position space, and I can literally change mu and it will just shift where is it centered at. K0 will define where is it centered in the momentum space, and sigma would be the width. And once the ansatz is optimized in each K sector, we just stitch together with this wave function and create the final wave packet creation of it. So the optimization part goes only for each K, and you can store these numbers. You can do it on a different day. You can store it. That's it. You figured out how the momentum state looks like, and then you just stitch it with the desired wave function and create the wave packet. So mapping, how is the algorithm and the circuit is done? So it's in 4 steps. The first one is how to map the fermionic and the bosonic degrees of freedom to the qubit, and it's pretty obvious. The bosonic links are mapped as it is because they are Z2, so only 2 states. For the fermions, we use Jordan-Wigner transformation to make sure that they anti-commute. And the mapping is showed here. And because of this, what happens if you look at the form of this wave packet, the final wave packet creation operator, which has both inputs and the optimized ansatz, can combine everything together and rewrite it after Jordan-Wigner, such as it is B-side dagger is expressed only in terms of raising and lowering operators sigma z's and sigma x's on fermionic and the bosonic Hilbert space with some coefficient c's. And these coefficients have now both input and the optimized parameters. And we will now show, I'll now talk about how to implement this B-side dagger on a device. From here onwards, I'll be talking about 6 staggered site, which has 3 physical, that means 3 physical sites and 3 momenta. We worked with it requires 12 qubits for the mapping and has only 40 physical states.
Every state you always prepare, always has a defined parity, right? because of your Jordan region, right? It's fairly bounded conditions.
Yes.
It's either global, even or global austerity always.
Yeah. Yeah. Yeah, there is some subtlety involved in terms of how do we take the Jordan-Wigner as well, but we can.
Yeah, exactly.
Yeah.
When you create one, you start from 0, go to 1, right? Then
Yeah.
the Jordan Wigner maps the coupling of the hadrons and stuff.
Yeah. And there is also the periodic term, which will make sure that, and there are those subtleties we've addressed it in the paper and we can discuss, but those are like for very the technical subtleties. The second step is preparing the ground state. So this is not the focus of our work, so I'll only talk about it briefly and show only the results. You can prepare the interacting ground state with whatever method you want to prepare it with. We used one which worked, and that's it. So this is the circuit where we got the motivation from this work, where they used the terms in the Hamiltonian itself to create interacting ground state. And in our Z2 gauge theory, that we use the hopping term. So each block is each hopping, and there are such blocks, and a diagonal term which is acted only on the bosonic degrees of freedom. And we saw that after performing VQE with only two parameters, one, the angle of the hopping and the angle of the diagonal term, we get the ground state pretty accurately, and we were happy with it. So it's gauge invariant by construction, because each term here is only restricted to the physical Hilbert space. It's a gauge invariant. And these are the results. So this is the VQE with the state vector evolution, so exact calculation. And this is the exact diagonalization. And they pretty much agree. The energy of the exactly diagonalized ground state and VQE agree up to fourth significant digit, fourth significant digit, and the fidelity, the overlap is almost 1. So in short, we have a very good ground state, interacting ground state to start with. The second is optimization of these momentum creation operators. So this is the result for the Z2 for k equal to 0 and k equal to pi by 3. The minus pi by 3 also has the same optimization results, because the answers is constructed in a way that k and minus k have, you just flip the k to minus k and you have the same result. But these, as you can see, it agrees very well with the exact diagonalized state, where the green circles are the optimized ansatz and the crosses are the exact diagonalized. Energies agree very well as well. And the fidelity is, for k equal to 0 is about 99%, and the pi by plus minus pi by 3 is almost 1. This is a parameter scan in the space. This is a scan of how well the optimization works for different parameters of the theory. So fermion mass and the coupling constant of the electric field. The darker the color, the better the answer has accurate overlap. And you can see it agrees very well. So yellowish, the yellower it gets, it means it's like the overlap, the 1 minus fidelity is about 10 to the power minus 1. This is for 6 sites. This is for 10 sites. For different, now 10 sites has 5 different momenta, and the corresponding parity, the k equal to 0, and the only positive ones are shown here. And there is this cyan line drawn on the k equal to 0 sector. This is because in the k equal to 0 sector, there can be a low energy state, lower than the mesonic states that we're trying to excite, which is created by just this gauge invariant U string, which has no fermions, but U particles going around. And since this kind of excitations, they are length dependent, because larger the lattice, more energetic they become to excite. And also dependent on coupling, larger the electric field Hamiltonian coupling, it gets the more energetic they get to excite. And as you can see it here, left to this line is where excitations like these have energy lower than the mesonic excitations that we're calling mesonic. Similarly here, and as you can see, the line got pushed if I go to the larger lattices. All right, so this is the result for the U1 lattice gauge theory with cutoff 1. It agrees pretty much everywhere in the different parameters. And again, there is the same line which has the excitations of the gauge field, just the gauge field going around.
Why is the 2 pi over 5 so much for something.
So in general, we've observed that the edges of the Brillouin zone, it gets worse because there are fewer momenta to add up to, right? So that's our current working hypothesis, but it needs to be checked for much larger ends. Yeah. Finally, the circuit.
You said that for the 40 states, is that 40K equals 0 states, or is that not projected on?
There are 40 states with different momentum.
Okay, so you projected on momenta would be even fewer states.
Yeah, in a particular momentum sector, yes. Yeah, 40 is the complete Hilbert space, no momentum projection. Yeah.
So in those plots where you have like the decomposition of the wave packets in terms of the configuration label, I think it's like 2 slides previous. Some
This
of those
one?
states it couldn't map onto because they have different K than.
Yeah, so most of them are a 0, right? So so these would be the states which under the translation symmetry will not belong to that K sector. Yeah.
For the K equals 0, do you know which one of those is the vacuum? Or
The number, I have a table at the end. Maybe we can come back to that. Like I have a table in the appendix. We can come back to that. So the goal is to implement this B-side dagger on the device, and it has 2 issues. First, it is not unitary, and the second, it needs efficient circuit design because there's these strings of sigmas which are entangling many qubits together. So let's address the first one, the non-unitary operator. We use the method provided in Jordan, Lee, and Preskill, provided by Jordan, Lee, and Preskill, which is if the operator has operator meets these 2 conditions, which is it annihilates the interacting vacuum, and also the commutation is 1, then one can construct a theta operator shown here with an ancilla, which is Hermitian, and if we create a unitary operator with a pi/2 angle and theta, where the starting point of the ancilla is 0 and the other configuration is the interacting vacuum, it can be easily shown that under these 2 conditions, the final state is the B-side dagger operated on the interacting vacuum and the ancilla goes to 1. And if the theta is a sum of many terms, then we can still apply this for trotterized version of it. And for the efficiency, we used a singular value decomposition proposed in this work by Dawoodi, Shah, and Stryker, in which for each theta mn, if it satisfies these 2 conditions, which is the squares are 0 and the singular value decomposition is known, one can construct these unitary operators U that can dress the theta from both sides, and whatever is left in between is a purely diagonal operator with the ancilla. So this is the construction we use. I'll show you the circuit designs for an example. But are there any questions here? And these 2 properties are true for our operators because they have fermion raising and lowering operators. If you square it, it's going to be 0. Yeah.
So can you use the B psi acting on the interaction vacuum to 0 as the condition to prepare your vacuum, or you prepare your B psi? Because I don't think you use that condition in your.
No. So as I said, the ANSAZ is designed that it projects out into the correct momentum because it has those phase factors. So I know that if I start with a non-zero momentum, it's going to be orthogonal no matter what, right? But if it is in the 0 sector, then we've seen that just because there are excitations which are non-zero in energy excitation, it's also, we try to do it with the condition that okay, have it orthogonal to the omega, but we didn't need it. It's just because the operator creates states which are orthogonal, which are more high energy, but k equal to 0 and a proper eigenstate. So that's why it's orthogonal. Yeah.
And you're saying this condition is also automatically true?
In this one, we'll address that later. But if I have BK daggers exactly known, right, then each BK dagger inside this B psi, each BK in this B psi will automatically annihilate the vacuum, resulting in B psi annihilating vacuum. And it will, and if the psi is normalized, this will also be true. Yeah, which is the outer wave function, which is of course normalized. So this is an example for the circuit. of a B dagger between 0 and 1 has some coefficient C01, which I already showed you, like is a result of both input and the optimized numbers, and it can be decomposed into the magnitude and the phase, and the phase part comes into the U operators, which diagonalize it, and this diagonal operator sits in between like this. So there are 4 RZ rotations which are needed. So this is the gate decomposition for one length meson operator. Finally, the hardware results. So this is the first plot where we have certain parameters for the theory as well as the wave packet. As the green circles are the exact calculated, and the stars are the ideal circuit. Ideal meaning the circuit is evaluated using the state vector method exactly, and has many trotter steps, because those theta terms when summed require trotterization. So it has many trotter steps, and you can see there is some deviation, and this deviation is coming from what you have asked, that because our answers is an optimization, is not the exact, there is some violation of this relation, and that's why the ideal circuit deviates a little bit from the exact one. The fidelity is still very high, and about the 3.8%. I mean, this number might be changed. This number might be from old calculation. I need to check on that, but yeah. So the next one is, because we couldn't afford to put the entire ideal circuit on a device because this is cost, we decided to truncate the circuit and only keep certain coefficients which are above a threshold in its magnitude. That meaning only the important terms are executed on the device. This is for the second order trotter with 1 trotter step, and we see that it's still about 95% overlap, and it's very close to the ideal circuit. Finally, the device result from the Quantinuum H11 system, which has 20 qubits, all-to-all connectivity, very high single qubit fidelity, and significantly high 2-qubit fidelity. Our complete circuit had about 300 C0 gates and about 350 single qubit gates. We performed only 500 shots. That's what we could afford to create two wave packets with different parameters. And there is no error mitigation required, except for the very simple one, which is if the final state is outside of the physical Hilbert space, we just throw it out. So our effective number of shots is lower than the 500 shots, but just from that, we get significantly good results. Any questions? All right. So this is the only observable which we could measure without doing any further operations on the state, which is the staggered number density, which is defined here. And as you can see, it agrees very well. This is because it's diagonal, and that's why we could only do it with the result available. For different parameters of the wave packet, we put 2 different wave packets on the device, and as you can see, it's a very nice agreement.
What does epsilon equal in terms of G for your couple?
So this is Z2, so epsilon is just the strength of the HE, but if you have to map it to the U1 theory, it's G squared over 2. Summary and outlook. So these are the 4 steps. We used an approach where the creation operators are optimized with an ansatz and directly in the interacting theory acted on the interacting ground state. There are the 4 steps of creating it, and these are the results. To emphasize, this is the gauge invariant construction of preparing states. So it's VQE based, and the systematic error is the error coming from the commutation, the violation of the commutation relations which we require. Works for U1 lattice gauge theory in 1+1D, and can be implemented on NIST devices with at least for the continuum minimum with minimum noise mitigation techniques. What's more, of course, we need more observable to measure the wave packet fidelity more than just calculating the number density. Analytical bounds on the systematic error, so to quantify how close are we to the desired state, and some advanced noise mitigation techniques if we want to go to larger qubit systems. What's next? Prepare two wave packets and scatter them, of course. The other is go to the U1 lattice gauge theory, where people in the audience have already figured out how to prepare the interacting ground state for very large systems. And finally, does the SunSAS work for non-abelian gauge theories, particularly for formulations of non-abelian gauge theories like the loop string hadron formulation, where the mapping of the ansatz seems intuitive. Thank you very much.
Question? Did you actually do them? I didn't get it. Did you do dynamics after you prepared?
Not yet. Not yet.
So
Just the preparation of the state. The devices are expensive. Like we could do it, we just didn't have the money.
the Azure,
What?
it's the Microsoft Azure thing
Yeah, yeah. It's the credits that
I negotiated.
yeah, you negotiated and then we used. So yeah, thank you. You are in our acknowledgements for that.
I don't have a question, but this was probably the most beautiful presentation I've seen.
Thank you. I get that often. Any questions on the Zoom?
I have a question.
Yeah.
Can you go to the, when you describe your way to apply the tag and the scale operator?
You mean the circuit?
Yes. No. Yes, have you tried? Yeah, because you have that, right? Have you tried to apply the linear combination unitary?
We haven't, but yeah,
Because
that was
based on the number of some German sum.
yeah. When we decided to implement this, we considered that method. But it turns out that if this is a condition that is obeying, like we checked this condition classically first, and it was very close. So LCU has this probability of success, right? We don't. So in this one, we don't need
So
that.
it's really one.
Yeah, yeah. It's just that the violation, like deviation from it, is very small because this is very nicely met. Yeah.
I also have a question here. So here you're doing this thing with like the ancilla to do this non-unitary operation.
Mhm.
But in principle, there's a unitary operator that could act on your system that would take you from the interacting ground state to your wave packet. Do you think there's a way to like learn what that unitary is to avoid?
Wait, is there a unitary operation which will always take you to the like the raising and the loading operators in any theory are non-unitary, right? Like you come up with some overall
Like a
factor.
unitary can take you from one state to any other state.
That is true. But in terms of this creation operator thinking, there is not. I mean, it's not obvious to think. So I don't know.
I mean, that's a property of the operator.
Yeah, it's a property of the P operator.
So if you know the input state, you only want that input state to go to the target state, right? So
Yeah.
unitary will do that. This is an operator that does the right thing for any state. He's just saying for that ground state, there will be a unitary
That will
to
take you
that
to-
ground state to an excitance. That will exist.
And how that will exist and how to think, like how to create that, like how to think about it. Is that your question? Like
Yeah.
how do you not? I haven't thought about it.
Do I?
You can kind of tensor network into a second.
Also, let me go through it, because this could be like a very like kind of grossly non-local thing, right? So I mean, if you try to actually do this on a device, like a million CMOS, that would kill you.
I don't know though, because your string operators are just acting on like 3 qubits, like the one that you showed.
Sure.
So it seems like you could construct a unitary that acts on those and gets the state that you want.
Maybe this is something we can discuss, but I've never thought about it. The reason was also because this way of thinking is very intuitive with the field theory way of thinking, right? So in that sense, I also felt that, let's say for the final point that I made for LSH, where we are trying to think about this in terms of the tensor network, right? It seems intuitive instead of thinking in terms of unitary it seems intuitive to think in terms of those creation operators directly. So generalizability is another factor, I guess, in terms of this way of looking at it. At least this is the way I see it, rather than like I'm not very used to seeing in terms of this unitary circuit on the quantum circuit.
Did you guys do this? With your meson?
We essentially like learn the unitary, I guess, is, let's do that.
So it's also like some sort of, you also parameterize that unitary with some parameters and try to like optimize it in some sense, right?
Yeah.
So it's kind of like the answers, but you're already building it in the unitary answers.
I think that's the way to go. I think. Because I mean, you want to set the wave packet directly in the vacuum.
Yeah.
Depends on how.
So the ingredients in both of those approaches would be the same, because any excitation, at least in 1+1D, that you can create are these mesonic excitations as well as those loops going around. And larger the lattice, the loops going around becomes more expensive, so you throw them out. And it's just that, like, okay, instead of starting with the Gaussian answers like we did, you can just start with a parametric answer containing those terms and make it a unitary gate, right? Like that's one way to think about it, I guess.
Any more questions? No? Let's thank speaker.
Yep.